So now that we have an idea on how to apply fragmentation principles to an actual problem, let's learn the remaining types of fragmentation here. What we haven't talked about so far is that even alcohols can homolytically cleave. And of course, it's going to happen in the same fashion that we've been seeing before. But let's make sure we see this. Again, we stick them in the mass spec, the electron beam dislodges this electron right here. We end up with this molecular ion right here. And what then happens is, let's focus on this particular alpha carbon. Notice it is the carbon that's directly bonded to the oxygen, just like with ethers. And look at this arrow movement, identical to what we've been seeing before. And notice it's the bond to the left of the alpha carbon that's being cleaved, and it's the bond to the right that's becoming a double bond, which ends up with these two structures right here. And notice also the fragment that results with the C doubly bonded to the oxygen is the one that's charged and is therefore the one detected by the mass spec. This means that our quick product method would also work for alcohols when it comes to alpha cleavage. Again, remember that means you're going to locate the alpha carbon, you're going to make the cut right here, and on the right side of this cut, the alpha carbon is going to be doubly bonded to the oxygen, and you're going to know that is the fragment that is detected. Now, let's look at another example of alpha cleavage here, but this time we're going to do it with a ketone. But again, as I walk you through this, make sure you see the analogous moves here. So it starts off with the electron beam dislodging an electron, in this case this electron right here on the oxygen, and that gives rise to this molecular ion right here. And notice we got our positive charge right here. That's going to influence this particular electron movement, which looks like this. And for now, let's just look at the aftermath here. What you would end up with from these electron moves is two structures that look like this. And while we're looking at this, let's point out the one that would be detected by the mass spec. Of course, it's the charged one, so we should expect to see a peak at 57 if this particular type of fragmentation takes place. But let's look at the other possibility here. We can get the same type of electron movement, but it'll be the bond on the left-hand side of the carbonyl carbon that cleaves. So for instance, if the electrons move this way, then we can expect these species as products. And in this case, it's the fragment on the right that would be detected, so we should expect to see a peak at 43. But notice what's happening here. Let's go back to the beginning here. All that's happening is really just alpha cleavage again. But this time the alpha carbon is the one that's doubly bonded to the oxygen. So let me show you how to do this type of fragmentation quickly when it comes to ketones. Again, you're going to start by locating the alpha carbon, and he's going to be always the one that's doubly bonded to the oxygen. And remember, in alpha cleavage, we're always cleaving the bond following the alpha carbon, which means we're going to break both the bond to the left of this alpha carbon and the bond to the right. Let's do the right-hand side first. Again, you're going to cleave this right here, and then you're going to look at this alpha carbon right here, and what you're going to do is place a new pi bond between that carbon and that oxygen. What that ends up with is something that looks like this. Notice now our alpha carbon is now triply bonded to that oxygen. And let's look at what happens on the other side of our cut mark. This carbon right here, he's going to become the radical. Notice this is also exactly what we've been doing before with all of our other alpha cleavages. So to make sure you got it, let's do it on the other side now. Again, we're going to end up cutting this bond on the left. We're going to focus on this alpha carbon right here, and we're going to add a new pi bond between that carbon and that oxygen, which means we're going to end up with something that looks like this. And then of course, on the other side of the cut mark right here, this is the carbon that's going to take on the radical. So notice we quickly alpha cleaved a ketone. However, there are also additional types of cleavage. Let's look at another type here. This type of cleavage involves both homolytic and heterolytic cleavage. And it's very specific to alcohols. And another name for this type of cleavage is called gamma cleavage. Let me show you how this works, and then we'll talk about a way to quickly do it. Again, it starts off with the electron beam dislodging one of the electrons on the oxygen, giving rise to this particular molecular ion. Now notice I'm emphasizing one of the hydrogens here in this molecule. It's actually the gamma hydrogen. Because again, using that same nomenclature here, this is the alpha carbon connected to the oxygen, that would be the beta, and this would be the gamma carbon. So we're looking at the hydrogen connected to the gamma carbon. If you have an alcohol that has this type of setup here, then here's what the cleavage looks like. The OH heterolytically cleaves like this. This is the heterolytic cleavage part of this process. But remember, we're saying it's also homolytic. Here's the electron movement for the homolytic cleavage. One of the electrons in the CH bond moves to the electron to the oxygen here, and the other electron in this bond moves up on top of the gamma carbon. Notice, look at the CH bond on the gamma carbon. That bond doesn't exist anymore. The two electrons left, it's being cleaved, but notice it's being homolytically cleaved. So it's the breaking of this bond that gives rise to the homolytic part of this gamma cleavage. Now, let's look at the aftermath here. What's happening is that this hydrogen right here, with its electron, is now going to be connected to this oxygen over here. So think about it. If that oxygen now has two hydrogens, he simply becomes water. And what's left on the other side here? Well, the remaining part of the molecule ends up being this fragment right here. Notice what's happening. It's the alpha carbon that's turning into a carbocation. And also notice it's the gamma carbon right here that's becoming a radical. Notice it's these features right here that help us with quick product. Again, if you have an alcohol that has a gamma carbon, then to quickly do this, you locate the alpha, beta, and gamma carbons, then you heterolytically cleave the OH off the alpha carbon and turn that into water. And the result is the alpha carbon becomes a carbocation and the gamma carbon becomes the radical species. And lastly here, let's point out which one of these is going to be detected. Of course, it's this one right here, the carbocation. He's going to be detected by the mass spec, so we should expect to see a peak at 70, whereas water is neutral and it won't be therefore detected by the mass spec. So notice gamma cleavage involves simply the loss of water. Now, just in case you might be wondering, why the gamma carbon? Why not the beta, or why not the one after it? Well, let me just briefly explain why that's the case here. Let's say you have this alcohol. Remember, this would be the alpha carbon, that would be the beta, and this would be the gamma. Remember, this is just a representation of this alcohol. Remember, these bonds are all single bonds, which means they can rotate, which means it's possible that this molecule could take on this particular conformation. And notice, let's again label our alpha, beta, and gamma carbons here. Notice it's the gamma carbon that actually is very close to the OH. Therefore, the gamma hydrogen is also close to the OH. And since these substituents are so close to each other, that's why it's these that form water, and this molecule therefore loses water. Now, let's look at the last type of fragmentation here. Congratulations, you made it. I know it may seem like a lot, but don't worry. With enough practice, you'll have all these down. This type of fragmentation is specific for ketones. And let me show you how it works here. We got our electron beam. It knocks out one of the electrons on the oxygen here, which ends up with this as our molecular ion. And for this type of cleavage, this is how we label our carbons. It's this carbon right here that becomes the alpha. He's beta and he's gamma. And let's do this. Let's emphasize one of the hydrogens on that gamma carbon. Here is our electron movement for McLafferty rearrangement. One of the electrons on the oxygen moves up here. One of the electrons in the CH bond meets up with him, which means this hydrogen right here is going to now be connected to this oxygen right here. However, there's another electron movement here. The other electron in the CH bond falls down between the gamma and beta carbon. And another electron movement happens right here. The bond between the alpha and beta carbon here, one of the electrons jumps up here between the gamma and the beta as well. And then lastly, the other electron in the bond between the alpha and beta carbon jumps up onto that carbon. Now, looks like a lot's going on here, so let's take this part by part here. Notice this electron movement means that this bond is going to be broken. So we're always severing the bond between alpha and beta. And this right here, these two electrons meeting up, means a new pi bond is going to be formed between the beta and the gamma carbon. Let's put what we have so far here. That would look like this right here. Now, what's the rest of it here? Well, remember, look at your alpha carbon. He has one electron jumping up on top of him, so he's going to become a radical. And we also said that the H on the gamma carbon is going to meet up with the oxygen, so the right-hand side of this would look like this. And again, who's going to be detected by the mass spec? Of course, the fragment on the right, because he's charged. So, quick product method here. Let's just develop it right now. Notice if you have a ketone, locate your alpha, beta, and gamma carbons this way. And all you're simply doing is severing the bond between the alpha and beta carbon. Do that first. And then represent the alpha carbon as a radical. And represent the oxygen as OH with a positive formal charge. And then all that's left here is to place a double bond between the beta and gamma carbon. And know that he is neutral and therefore not going to be detected. So, what have we learned here? Well, definitely a lot. Okay, but let's look at our key points. Number 1, there are 3 general types of fragmentation: heterolytic, homolytic, also called alpha, and McLafferty rearrangement. We also saw that 2 halogens, ethers, and alcohols can cleave heterolytically and technically homolytically via alpha cleavage. We also saw specifically that alcohols can fragment by a loss of water. And the last type of fragmentation we saw was that ketones can fragment homolytically and via McLafferty rearrangement. And just as important, we saw how to quickly slice and dice these molecules to generate all the possible fragments and to make a prediction on what we might observe on a mass spec for given molecules.